So here's the last problem. It's got a lot of steps, but I think you can do it. So I'm going to lower the boom to 30 degrees, which means the weight is hanging even further away, so the distance is going to be greater. It's the same weight, bigger distance, bigger torque. Now we have to figure out how much counterweight we're going to add to the end of the crane to make sure it doesn't tip over. So the first step is, well, the torque of the crane is the same as it always was, 174.25 inch-pounds. So first we need the torque of the load. The load is hanging down here, even further away. So we need the distance from the line of force, which will be here, to there. And that's going to be, and don't forget it's at a 30-degree angle. Now remember, when we had the boom at a 60-degree angle, so this would be the boom, and this is the distance we wanted. We multiply the boom times 0.5 to get the distance. Then when the boom was at a 45-degree angle, same idea but a different number. We multiplied the boom, or the hypotenuse, by 0.707, and that gave us the number we needed, the distance from here to wherever it was. Now we're 30 degrees. Let's see if I can get this in here. So instead of multiplying by 0.707, we got a new number, 0.866. So the hypotenuse times that gives you the answer. And the boom is 46 inches, so we multiply that by 0.866, and we get 39.8 inches. So that's the distance, but not really. Don't forget, hold on a second. That distance was to here, but we have to subtract the 10 inches because this part of the load and the boom is on this side of the pivot point. We're only interested in this side. So we take off 10 inches from that 39.9 and get 29.9. Really need a helper here. Okay. Well, let's see if you can do it in your head. So the distance is not 39.9, but it's 29.9. Let's round that off to 30. Weight times distance. 30 times 9.4 gives you 280.12 inch-pounds. So that's the torque of the load. Now we haven't talked about the torque of the boom. I haven't used that before for various reasons. But we're going to do it now. So we got 280.12 so far of torque. Now for the boom. The line of force of the boom goes through the middle of the boom. If this is 46 inches long, halfway is 23. So now we have another triangle, a 30, 60, 90 triangle. But the hypotenuse is 23 instead of 46. We use the same formula. The hypotenuse times 0.866 gives us the distance. 19.9 inches. Let's round it off to 20. But again, we have to subtract 10 inches from that. So we've only got 10 inches. So the distance is 10 inches. And the weight of the boom is 2.2 pounds. So 2.2 times 10 is 22 inch-pounds. So the torque of the boom is 22 inch-pounds. We add that. Remember the torque of the load? What we got. When we add the two together, the torque of the load and the boom, we get 103.12 inch-pounds. So, remember with that safety factor idea, if we've got 302.2 inch-pounds of torque here, we have to have a lot more here. How much more? 1.5 times more. So we multiply the 302 by 1.5 and get, you should check me, maybe my calculator's wrong. This times 1.5 gives us 453.18. Now how much torque do we have in the crane body right now? We don't have 453, you've only got 174. So you know it's going to tip over. So we need 453.18, and we have 174. So we subtract the 174 from the 478. This would be a lot easier if I had somebody helping me. All right. We subtract the 174 from the 453. That's what we got. So that's the additional torque we need to conform to the safety range, make sure nothing's going to tip over. So, torque is weight times distance, remember? Here's the torque, and the weight just happens to be 5.7 pounds, because all I've got is a brick, 4.7 pounds, and one clamp, 1 pound. So 5.7 pounds. You think it'd be okay if we hung it there? Well, hold on, I got to get the load. What do you think? Is it gonna work? It's working, but we don't have a safety factor. Remember, if I swing the load or something else happens, it's going to tip over. So we need more counterweight. We don't have any more counterweight. The only thing we can do is, instead of increasing the weight, we can increase the distance. So if there's some way I can mount the counterweight further away, that'll do the trick. First we've got to figure out how much further away it should be. Keep track of my posters, will be okay. That's not it. There we go. Now we sort of compute in reverse. We need this is the torque we need, 278.93. Torque is weight times distance. Well, we have the weight, 5.7 pounds. All we have to find out is the distance. If we divide this by 5.7, we get 48.9 inches. Remember, distance times weight equals the torque. We divide this by that. So 48.9 inches, let's call it 49 inches. Now, we only have the end of the crane is only 40 inches from the fulcrum. From here to here is only 40 inches. So I'm going to take another piece of wood, a cedar. I use cedar because it's lightweight. Now normally we would have to include the weight of this board in our computations, but not today. So I'm just going to attach this board here. And I put a mark here at 50 inches to be safe. So we have the added torque of this counterweight, 5.7 pounds times 50, let's say 50 inches. So now we're well within the safety range. So remember, if torque is weight times distance, if you increase the weight, you increase the torque. If you don't have any more weight, you have to increase the distance. You didn't see that. No problem. We've got a good safety factor of 1.5. Crane's pretty long, but it works. Now you could probably do the same thing with, recompute everything with the boom at 45 degrees. And we already did that, I think.